This is a brief introduction to getting your hands on real astronomy data. In order to give you an overview of what I'm going to cover, I'll have a couple of slides on how to get access to real data through citizen science projects. Then, in order for you to really understand how to use astronomical data, I need to give you a basics course in several different concepts. One is the format in which the image is stored and why it matters. Then we'll talk about a whole bunch of things having to do with astronomical images, including color, tables and stretches, artifacts, and spatial resolution. I work for IRSA, the Infrared Science Archive at Caltech, IPAC, so that's the archive with which I'm most familiar, and so I have some screen grabs of a tool at IRSA that I can specifically point you to. And then, because I'm going to be covering a lot of things pretty quickly, really important ideas have a box around them. I do have a web page that has a copy of this talk, as well as a list of all the links that are mentioned in this talk. So for citizen science, there's lots and lots of programs out there, including many, many astronomical citizen science programs. Most of these programs are entirely web-based. In other words, you don't need anything special installed on your computer. You just need a web browser. And you don't have to have a really deep knowledge of the astronomy, the astrophysics, or even how the data were taken in order to participate in the science. Some of the citizen science programs have lesson plans or labs or exercises that allow you to incorporate them into a class you're teaching, or share it with your children or your nieces and nephews. The best is citizen science programs have hooks that you might not notice if you're a beginner, but they're waiting for you when you're ready to go deeper. There's many choices. Zooniverse is one of the biggest organizations that produces these, and so they have a ton, not just in astronomy but in all sorts of fields. You can go to the list of Zooniverse projects and just scroll through the list. One of the oldest citizen science programs is something called SETI at Home, where they're looking for extraterrestrial life, basically in radio signals obtained from other stars. There's also something called International Observe the Moon Night, which involves just moon watching, which means you can even do it from here in LA. Globe at Night deals with light pollution. There again, you can do it from wherever you are, whether it's in the city or the country. There's also something called the Great Worldwide Star Count, which is also related to light pollution. Stardust at Home is looking for dust particles in aerogel. Something called Citizen Sky is actually part of something called the AAVSO, the American Association of Variable Star Observers. They specifically focus on variable stars, and they have an amazing infrastructure where you can learn how to contribute data to the scientific community. There's something called CosmoQuest, which deals with lots of crater mapping projects, among other things. I'm sure that I'm missing some, but this is just a screen snapshot of the Zooniverse menu of astronomy projects, just the astronomy projects, and it might even be out of date. When you go into any of them, the first thing that you'll see is a short tutorial that it basically shows you, okay, this is an example of what you're looking for. This is how to do what we're asking you to do. And so if you actually create an account, then you don't get this tutorial every time you log in, but you can access it whenever you want. And then you can contribute on whatever timescales make sense to you, sitting in front of the television, working on your laptop, or whatever you want. This is another interface to a Zooniverse project. Again, it's launched into the tutorial that tells you, okay, this is what we're looking for, right? Usually the tasks they're asking you to do are not so hard. And there's lots of tutorials that have been developed to help you figure out what it is that they're asking you to do, which means that even little kids can participate just like grown-ups do. And key to understanding your participation in this is that you don't have to be perfect. The reason the citizen science projects work in the first place is that they have 5, 7, 10, maybe 20 people looking at each item. And if you make a mistake, that's okay, because most of the other people looking at it are going to get it right. So even if you get it wrong, especially when you're learning, it is okay, because mistakes are going to average out. Why are they going out of their way to make these data available and these tools available? Well, because it turns out that even with as sophisticated as computers are getting, the human eye is still really good at finding patterns, and it's good in such a way that it's often really much better than what the computers can do right now. And you are contributing to real science in the sense that it does produce real journal articles. These are just some of the journal articles that have come out of some of these citizen science projects. And you notice some of these have really long author lists. That's because they're including all of the amateurs who helped with this citizen science project. So if that's absolutely the only thing you remember from this talk, and especially if you really get into one of these citizen science projects, then that's awesome. And I've really done my job, and you don't have to listen to the rest of it. But maybe you realize that that's just the tip of the iceberg, that there is a lot more data out there. So that's what I'm going to start talking about next. We're going to go down the digital rabbit hole here. So it is really true that there are more astronomical data available right now than professionals can hope to completely mine. And there's more data coming in all the time, and new facilities coming online all the time. Now, professional astronomers are often going to pull off the easy stuff, but that doesn't mean that there isn't good science left in the archive for you to do. Any facility, any US-based facility that comes from government funding is supposed to have a publicly available archive. So that, because these are your data too, that means that you have the right to access all of this data through the archives. NASA is really good about having archives. NSF is getting there. Europe is getting there. There are other countries that don't really buy into this idea that data should be public. But NASA data alone is going to keep you busy for a long time. They have data that sort of fall in three large categories. Astronomy data, like astrophysical things like beyond our solar system. Then there's moon and planetary data from within our solar system. And then there's a whole huge host of Earth observing data. I know the astronomy data the best, so that's what I'm going to focus on here. But I wanted to call your attention to the fact that this is just part of a vast universe of data that's out there. So the archives that are developed are designed at the end of the day for the professional astronomy community. But that professional astronomy community is going to include everyone from an emeritus professor who can barely read his email all the way down to a summer student at the beginning of her professional astronomy career, and everybody in between. So that means that when we design archives that are easily accessible by that range of people, you can get into it without too much pain. But you do have to reach across the barrier. It's not going to be served up to you on a silver platter with a nice vase with a rose, right? You're going to have to meet me halfway here. You're going to have to become familiar with some jargon, some conventions, and you're going to have to work a little bit to get up to speed. But the truth is that because these archives are available to a wide range of professionals, you can get into it without too much pain. So the first big concept I want to cover is just don't use Microsoft Internet Explorer. Just don't do it. Just ditch it. Go get Firefox, go get Chrome. The browser that comes with the operating system on Windows machines is just buggy, and it has huge security holes. Most astronomers are on Mac or Linux machines, and so we're not using Internet Explorer in the first place. And because most of the archives are operating just, with the barest trickle of money, we don't have the resources to make these web-based tools work on Internet Explorer, especially since so few astronomers use it. So often Internet Explorer support is just dropped. So there's some archives that won't even work if you have that as a browser. So just don't use it. Go get Firefox, go get Chrome, use one of those. The next big concept is the idea of how an image works. So all digital images are ones and zeros. They're all, at the end of the day, they come down to stacks of ones and zeros. It's just that your computer knows how to display those ones and zeros to you in an image form. Images that you save from your digital camera, whether that's your cell phone or more professional single lens reflex digital camera, those are usually stored in either JPEG or GIF format. Sometimes they're PNGs, but JPEGs and GIFs in particular are typically 8 bits deep. What that means is, for each level in each pixel, you have only 2 to the power of 8 discrete levels of information. So what that means is 2 times itself 8 times is 256. So there's only room in each pixel for up to 256 ones or zeros. It doesn't have more, it doesn't have less, it's only 256 for each pixel that you have. And then there's another ramification for color planes. We'll talk about that in a little bit. Now, normally you don't care about this. The people that do care about it include graphic designers, web developers, and astronomers. So that 2 to the 8 bits deep, that's called dynamic range. Astronomical images have much greater dynamic range. They have 16 bits or even 32 bits deep, which so that means is 2 to the power of 16, 2 times itself 16 times, or 65,536 possible levels in each pixel, and even 2 to the 32, 4.3 billion discrete levels of data in each pixel. So when you have an astronomy image, it comes to you as either 16 or 32 bits deep. If you turn it around and save it as a JPEG, you're going to lose information because you're asking the computer to compress 65,000 levels into only 256. And so the image often doesn't look very good. It may not look like it does on the screen even. So another way to think of the bit depth, I was scraping around trying to find a good way to explain it. And I can think, okay, what holds just a little bit of water? A thimble. Okay, so I'm going to have an array of thimbles. And each one of these thimbles can hold just a tiny dribble of water, up to 256 drops. And if you put more than 256 drops in each thimble, it's going to overflow. And that's totally fine for images you take with your cell phone. You are not going to notice any differences. But astronomy images have more capacity in each pixel. So the closest thing I can think of was teacups, an array of teacups, because now each of these teacups can hold more than a dribble of water, but they still can overflow. So I'm scraping around on the web trying to find a better explanation. Oh, trash cans! Trash cans are even bigger. So now instead of an array of thimbles or even teacups, I'm going to have an array of trash cans. And I can hold lots of water in each one. 65,000 drops of water or 4.3 billion drops of water, say, per can. So that's the difference. You're talking about thimbles versus trash cans. So images from your digital camera are 8 bits deep, which means 256 drops in each bucket. 16 or 32 bits deep means that 65,000 or 4.3 billion drops of water can fit in each bucket. And in your camera, it turns out you have one array of buckets for each color. We'll talk about that in a second. The analogy with the buckets of water is imperfect, but it does really do okay. The basic idea is that, you know, when you see ads for cameras with a certain number of pixels, that's talking about how densely the buckets are packed together and how many total buckets there are. But I'm talking about how deep the buckets are. That's bit depth. So if none of that still makes any sense, the key concept here is that there's more information in astronomical images than there are in JPEGs or GIFs. Now, JPEGs in particular are pretty sticky. They are something called lossy compressed. They compress the data, and the file takes up way less disk space, but it loses information. That's what lossy means in lossy compressed. So you can see an example here on the right that I actually took from Wikipedia. So there's a low compression JPEG here where you can see even the hair on the edge of the cat's head. Here we have high compression, which is low quality JPEG, and you can see it's blocky and you can't really see individual hairs on the cat's head, and there's sort of ringing around the edges of the cat. I mean, this is kind of like the idea between HD and regular resolution TV, right? There's just more information in the low compression, high quality image. When you're talking about astronomical images, someone worked really hard to collect all those photons. So don't do this. Don't lose information at the very last step. There are some kinds of compression called lossless compression, and that's okay. But you don't want to lose information. You don't want lossy compressed images. So what that means is, if you do want to play with real astronomical images, you should not be using JPEGs, GIFs, or even PNGs. You should be using another format. You should be using something called FITS files. FITS stands for Flexible Image Transport System. It was developed decades ago, and it's exactly what that acronym stands for. It allows you to flexibly take images from different telescopes and different software packages and still be able to read the images. Most professional astronomers use this format. There are some that use other formats, but most people still use FITS. It's not compressed. There's no loss of information. FITS images have a plain text header and then the binary image below. So if you try to drop a FITS image into a text editor, it will look initially like it's readable because it'll have the plain text header. But then when you get to the binary, your text editor won't know what to do with the binary image, and it'll just give you the array of strange characters. The header of the FITS images is where you have something called metadata, which is information about the data, hence metadata. It's got things like the coordinates of the image, where you're looking in the sky, and it could have things like the target you were looking at, what telescope you used, who took it, what observation time and date you took it, what wavelength it's in, and then there are some headers that can get really long because every data reduction step adds at least one line to the header. So it can be really rich or it can be very terse. At the very least, it usually has the coordinates of where it's looking and how to translate pixels to coordinates on the sky. The binary image itself is usually just one image plane, but it can be many different planes. It can be, say, errors, the image and then the errors and then the coverage, and it can be additional planes. And technically, you can also have FITS files that are data tables. Sometimes those are spectra, list of wavelength and brightness. It can literally be a data table. You need to have, of course, software that can read FITS images, but astronomers are a really big fan of free software. So even though you might have heard of something called ImageJ that can handle FITS, I don't know if that's free, to be honest with you. MaxMDL is really popular in the amateur astronomy community. That's not free. Photoshop is not free, but it has a free plugin called FITS Liberator that can handle FITS images. But because astronomers really do like free software, there are tools from IRSA that I'm going to show you, but you can also Google DS9. I don't mean the Star Trek show, although the meaning is not divorced from that. That's a separate talk. But you need to Google DS9 with Harvard to find that software. And if you speak Python, there's a whole bunch of Python tools that allow you to read FITS images as well. And I'm sure there's other packages out there, but those are the big ones. All right, next big concept, using color in images. So remember, we've got our array of buckets, whether that's thimbles or teacups. Let's go with buckets because we're using an astronomy image. We've got, big buckets of light. How are we going to display the water levels in those buckets? How are we going to represent the numbers, the amount of electrons in the pixel, the amount of water in the buckets? How are we going to represent that on our screen? So to explain that, I'm going to take a brief historical detour. This is the first image from Mars. It was taken by Mariner 4 in July 1965. And there's something interesting about this. If you look really closely, you can see that it's a stack of paper that's colored in, full of 1s, 0s, 3s, 2s, that's colored in. And the reason for this is that when those images were coming back from Mariner, computers, remember, in 1965 were pretty new. And so it was going to take the computer hours and hours and hours to turn all that binary data into an image. The scientists and engineers were way too impatient for that. So they printed it out, stacked it up, and colored it in. You think I'm kidding? I'm not. They printed it out, they stacked it up, and they colored it in. This is the color scheme that they used. It turns out that they actually ran down the street to an art store that actually turns out to be not too far away from where I live, and they were trying to find a set of pastels that they could buy, not too expensive, that was going to give them a range. They wanted at least 6 different colors of gray, because that's what they were going to get back from the computer when it finally coughed up the information. It was going to give them a grayscale image. But they couldn't find any pastel sets that had 6 shades of gray. So okay, fine, we're going to use this brown-red scheme. They didn't know, of course, that images from rovers on the surface of Mars were also going to have this color scheme in the end. But this is the very first image that was ever returned from Mars. So they didn't know what they were going to find. They could have, depending on what pastel set they bought, ended up with 6 shades of green or 6 shades of purple. It just kind of worked out that they have sort of a red-yellow color scheme. So there on the left is the image that they colored in. And there on the right is the image that eventually came back from the computer, from Mariner. And it's not horrible. It's not great, but it's not horrible. You can see there's definitely similar structures in these 2 images. So it really wasn't so bad. It actually worked pretty well. So this is literally a color by numbers situation. So within an image, you can assign a number to a color. So if you have these 9 possible different values, you could color all the 1s purple, all the 2s blue, all the 3s light blue, and so on. But what do you do if you have values more than 8? And we've talked a lot already about having buckets that can handle more than 256 drops of water. So what if you have numbers more than 8? Okay, let's spin them up. 0s and 1s are black, 2s and 3s are purple, 4s and 5s are blue. Now we can at least show more data ranges between 0 and 17 now, not just 0 to 8 like we had before. But what am I going to do with 7.9? 7.9 is technically, according to this, a blue, but it's closer, certainly, to green than 6 would be. So what color should I make 7.9? Okay, we'll make this continuous. Now we have a continuous spectrum of colors that's not discrete. There's no clear boundaries between the colors. Now we have less blocky color. But what if we have numbers more than 17? Well, we can do something different. Like we can put all the ones that are 10 to the 0, which is 1, and 10 to the 1, which is 1. So all the values between 0 and 10 are in this bin. Between 10 and 100 are this bin. 100 and 1,000 in this bin. And so on. Now we can display a much larger range of numbers. But key to all of this is in all of these examples, we are still working with just one image. Values from just that one image are displayed as a color, and you get to pick what the correspondence is between the value in the image and the color that you display on your computer. So color tables, that is the range of colors that you're mapping those data from one image. There's many different ones. The ones that I was showing you initially were this, which is very discrete values of color. Then there's this, which is more continuous. This one is continuous, but between black through reds and oranges to white. There's lots of different color tables that are out there. Color stretch describes how you're going to translate the numbers into colors. So the examples that I gave you were like this. And this is a linear stretch. That's something called a logarithmic stretch because I'm using powers of 10. But there are many others that you can use. So one image can be represented of shades of gray, or like for the Mars image, shades of red and brown. You get to pick how those numbers are mapped to colors and exactly what colors they get mapped to. But astronomical images, especially ones taken in just one filter, are often shown either just in grayscale or reverse grayscale, in part because it's the least distracting way to display details. Also, if you print it out, it doesn't kill your printer toner cartridge. But there's the same image. One on the left has bright white being bright in the sky, and here we have black as being bright in the sky. So you can see it's the same data, right? And it's even the same stretch. You can still see the things that are in both images, but your eye is drawn to different things in the reverse grayscale than in the grayscale. So color images, this is a biggie. Turns out there is no such thing as a color image. What, you say? No, it's true. So what we're going to do here is we're going to take one image, and rather than scaling it to shades of black to white, I'm going to scale it from black to red. Now I'm going to take another image. I'm going to scale it from black to green. Now I'm going to take another one and go from black to blue. Then I'm going to stack it up. This is how color images works. This is how your TV, your computer, your camera, the projector, this is how all of these devices construct a 3-color image. So an object that's faint in all 3 wavelengths that you pick is black, and something that's bright in all 3 is going to be a combination of the red, the green, and the blue, which is going to end up being white. All color images are made up of 3, but sometimes 4 separate images. The oldest color photographs, that the innovation that the color photographs brought over the black and white photographs, is that there are stacks of 3 emulsions, a red one, a green one, and a blue one. In other words, there's an emulsion that's sensitive to red light, an emulsion that's sensitive to green light, an emulsion that's sensitive to blue light, all stacked up. Digital cameras or TVs literally have 3 sets of pixels all interlaced. Sometimes you can have 4 sets of pixels for cyan, magenta, yellow, and black, which is CMYK as opposed to RGB. Astronomical images, when we're doing this, have different filters that you apply to the data. So this is an example of 3-color image printing from 1902. They have a red, yellow, and blue plane That's all combined together to make a 3-color image. This is what, if you get up real close to your TV or your computer screen or your cell phone screen with a magnifying glass, this is what you'll see. Arrays of red, green, and blue pixels that are all interlaced so that when you see them together, your eyes blend it and give you the illusion of a 3-color image. But in astronomy, you're taking an image in just one filter at a time. What does that mean? Filters are vaguely kind of sort of like colored cellophane. What I have here is theater gels. And they only let in light. For example, this one only lets in light that's red. This one only lets in light that's green. And this one only lets in light that's blue. So when you do an astronomical image, you take an image through the red, an image through the green, and an image through the blue, and then you stack it up. So the whole reason for filters is that you are limiting the amount of light that's hitting your detector, because you're making the light go through the filter before it hits your detector. So I'm only measuring the light that makes it through the filter. So you take an image in one filter, you assign a color to the image from that filter, and you do it again. And you do it again. If you have an RGB image, you do 3. If you have a CMYK, you can do 4. Conventionally, the shortest wavelength is blue and the longest wavelength is red, but you can do whatever you want. As long as you tell people what you're doing, you can do whatever you want. So you get to pick not only how you map the colors to the numbers and how you map, how you describe that stretch, how you turn those numbers into colors, and you get to pick exactly what colors they map to. And how you do that depends on what details you want to bring out in the image. Maybe you're interested in the faint stuff around the edges of a galaxy. Maybe you're interested in the very bright core. You might use very different stretches depending on what you're looking for. There's lots and lots of public images that are described as either true color or false color. True color is just a really confusing concept because everybody's eyes are a little bit different. And Emily Lochdoel has a very interesting blog post where there was the same day in 2015 where 2 different images taken by 2 different lunar orbiting spacecraft were released, and both of them claimed to be true color, but they were both different. So she's got a very nice blog post talking about that. I don't like the term false color because it makes it seem like we're lying or hiding something. But if I have a whole bunch of images that I took of the sky in infrared, which is sort of redder than red light, you can't see it with your eyes. So a true color infrared image would be super boring. It would just be black. So I have to make a translation between the numbers that are in the image and colors that I can see with my eye. So instead of true color or false color, I'm going to use the term representative color because that's what I'm doing. I'm taking the data that I have and representing it as light that my eyes can see. Some people have this misconception that you collect the data first and then break it into colors later. But it's really not. It really is taking them separately. It's true that we've been talking a lot about taking one image and changing the color table. And so, yeah, you are kind of breaking it into colors. But when you're talking about making a 3-color image, you need 3 different images. And you take something for the red plane, something for the green plane, something for the blue plane. So unless you have a really, really sophisticated instrument, you can't separate the photons after you record them. So you have to take the images in each filter separate. All right, astronomical data. I've already mentioned a little bit about multiple wavelength. We're studying multiple wavelengths. We're studying things we can never visit, and you can't pick it up and turn it around and see what it looks like from another angle. So we have to get really creative about taking advantage of all the light we get from these things, even the light that doesn't make it through the atmosphere, even the light we can't see. So there's lots and lots of telescopes and data, and therefore archives of data from the gamma ray all the way through the radio. At IPAC, we study lots of infrared things. And so this is the way that we look at the infrared spectrum. This is the way that we look at the electromagnetic spectrum. So, sky coverage and resolution. Not every telescope looks at every single thing in the sky. Some telescopes are designed to do that. They're surveys, but most are not. They are looking specifically at specific objects. So if you just go out there and grab any given archive, your favorite object may not be in there. Different telescopes are going to use different wavelengths of light, but different telescopes also have different pixel sizes. So when you're talking about a pinpoint of light like that from a star, it may look like a truly a pinpoint to one telescope, but a blob to another telescope because it has different pixel sizes, which means different spatial resolution. And sometimes that's real astrophysics. It looks like a pinpoint in optical, but a blob in infrared for a reason. It's not just the physics of light and the detection of light at the telescope that causes that. So here's the most famous image. It's been downloaded from the Hubble archive. It's the talons of the Eagle in the Eagle Nebula, or M16. It got dubbed the Pillars of Creation because this is a giant star-forming region where there are, lots of baby stars being formed in this larger region. This is an RGB image. So they have 3 narrowband filters here. Blue is oxygen 3, a forbidden line of oxygen 3. Green is H alpha, and red is a forbidden line of sulfur 2. So this image is tiny. This image is just 1.2 arc-minute square. That is the larger region taken with a telescope that I work for called Spitzer. And this image is a 4-color image. It's a CMYK image, so 4.5, 8, 24, and 70 microns. But that tiny footprint for the talons of the eagle is that whole image, and you can see Spitzer's got a much larger area. That's what IRAS saw. IRAS was the very first infrared survey mission. It was a satellite in the 80s. It's lined up right, I swear. You can see the darker regions in the lower right and the brighter regions in the upper left. It's lined up. It's just that Spitzer is a recent telescope, it's still flying, and IRAS is an old telescope that's no longer working, but it was the first one. So this is a vivid example of how there's different spatial resolutions of things in the sky. There's the Spitzer image again. Now we're going to look at even longer wavelengths. So this is a Spitzer image. Again, it's 4 colors, 4.5, 8, 24, and 70 microns. So 70 microns is the longest wavelength here, so that's the red. This is a Herschel image. This is a 3-color image. 70, 160, and 250 microns. So 70 is the shortest wavelength here. That's the blue. Here it's red, is 70 microns. Here it's blue. So you can look at much longer wavelengths. But we're also looking at mostly dust. There's lots of point sources, lots of stars in this, and it's mostly not point sources, it's mostly dust. But look at that, look at the talons from the eagle right there. You can see that it's changing spatial resolution. It looks a little bit fuzzier in Herschel. This is from WISE. It's again at the same scale. You can see that the talon is even fuzzier. But the WISE mission is a survey mission. So there's no end to the WISE data. It covers the whole sky. Images like this, that's pretty much the entire mosaic that Spitzer got of this particular region. But there's no end to this data. So if you were interested in studying how the Eagle Nebula fits into its surroundings, how it relates to other things that are in the galactic plane, you can do that with WISE data. So even though it's fuzzier, it covers the whole sky. That's usually your trade-off. Usually if you want high resolution, you don't get a lot of sky coverage. And if you want lots of sky coverage, you usually don't have high resolution. Last big concept, artifacts. When you are getting into these archives, you are working with real data. That means it's not been prettied up and polished for distribution in a big press release. There are going to be artifacts. That means stuff that isn't really part of the sky. And it could be how the telescope responds to light. It can be a plane or a satellite moving through the image, or even dust or bugs. Many big images that you find in these archives are actually lots of little ones. Those images of the Eagle Nebula I just showed you, those are lots and lots of small images knit together or mosaicked together. And depending on where you're getting the images, you might be able to see those boundaries between the tiles. It'll end up looking sort of like a patchwork quilt. It's not supposed to. Sometimes it does. You are familiar with artifacts because if I show you this, you are never going to assert that these bright lights at this high school football game have giant purple wings hanging off of them and one has streaks coming down to the ground. No, you're never going to assert that. That's because you know that those things in this image are artifacts, meaning they're not really there. It's a result of how the camera is responding to those very bright lights. And that's the same thing that happens in astronomical images. There are features that are just a result of how the telescope and the instrument and the detectors respond to bright point sources of light. Sometimes it's responding to a bright source that isn't even near the image that you're looking at because of scattered light in the telescope. So you have to be aware that there's artifacts in these images. So I'm reminded of a time that Neil deGrasse Tyson went on Stephen Colbert, and Stephen really wanted to talk about this star that people were wondering if it had alien structures around it. And Stephen really wanted to talk about that. And Neil cut him off with, "Wait, no, excuse me. Just because you don't understand what you're looking at doesn't mean it's aliens. If you find something that looks weird, do not assume that it's really in the sky. It is much more likely to be weird artifacts, like a result of saturation or scattered light or a plane or spatial resolution problems, or there's a very bright source in the wrong place. You need to actually get educated. You need to read the documentation and understand what the artifacts are that could be affecting what you're seeing. You need to educate yourself, and then as an example, you could try to convince a friend that it's real and not an artifact. Don't call me and tell me that you've found evidence of alien life that the government has been hiding. I swear, if there was alien life, astronomers are the worst secret keepers ever. You would know about it. It's not aliens. It's not giant space praying mantises. It is probably an artifact, like this bug that's caught on the window to this instrument. So, keeping that in mind, let's go look at some real archives. So there's many astronomical archives that are part of NASA. I work at IRSA, which is based at Caltech, and that's NASA's home for infrared and longer wavelength missions and data. We have some non-NASA data, and we have some data that's not infrared, but that's our primary mission, is the NASA infrared and longer wavelengths. The Exoplanet Archive is also based at Caltech, and as their name suggests, they focus on exoplanets and the stars that host them. There's something called NED, which is the NASA Extragalactic Database, that is also at Caltech. It focuses on galaxies. MAST is based in Baltimore at Johns Hopkins and Space Telescope Science Institute. That is primarily optical data from NASA. Something called HEOSARC is based at Goddard Space Flight Center in Greenbelt, Maryland. That is high energy NASA data, so like X-rays, gamma rays. There's something called ADS, which is the Astronomical Data System. It is all astronomy literature. And by that I mean from the 1800s through this morning, it's all there. Astronomers are totally on board with this open access stuff. You may not be able to get the beautiful typeset version from the journal if it's a new article, but all the content is posted in an archive called AstroPH, and ADS indexes all of the formal published journals as well as AstroPH. So everything is there. There are other archives in the US and other archives in Europe and Canada and Asia and India, but I don't know a lot of those very well. I really mostly focus on IRSA because that's where I work. IRSA is physically located at Caltech, and we are running rapidly towards petabytes of data. Remember that a petabyte is 1,000 terabytes, which is a petabyte is 1,000,000 gigabytes. This is a huge amount of data. We have several all-sky surveys, and we have pointed observations that cover just, observatories that go just where you point them. And so that means we have both big and small data sets. Many of the biggest data sets that we have are in the same sort of interface, so that once you master it, you can easily get access to other data that we have. I'm going to point you towards a tool called Finder Chart, because it gives you the same chunk of sky in many different wavelengths from many different surveys all at once. That's the URL, but there's also a big button on the IRSA homepage that will take you to Finder Chart. So that's what it looks like when you load it. The first thing you need to put in is a name or position of the object that you want. Right now, it doesn't handle solar system objects, so if you put in Jupiter, it'll go, huh? Okay, so you don't want Jupiter. You want things that have right ascension and declination, positions on the sky. So like M16 or M101 or specific right ascension and declination. If you put in a name, it will echo below the box the position that it thinks you're asking for, just so that you can check. Then you need to put in the size of the region that you want. It comes up by default in 300 using 300 arc seconds, and that's fine probably for most purposes, but you can go up to a degree or down to a couple of arc seconds. This is a pull down, so you should put in the units first and then the numbers. So because if you put in 1 thinking you're going to do a degree and then change this to degree, it will convert an arc second to a degree, and that's not what you want. You got to pick the units first and then put in the number. This just refers to how big the image is on the screen. That is all of the surveys that you have available, and I'll list which wavelengths those correspond to in a second. I would recommend turning off the catalogs until you're ready to really deal with catalogs. So the different surveys, there are 2 optical. So DSS is the Palomar Observatory Sky Survey. It was originally taken in the 1950s, and what we're showing here is digitized scans of those photographic plates. There are 3 of them, a blue, red, and a near infrared. Optical, and there's also a second generation of DSS that was taken more recently in the 90s. There's also an optical survey from the Sloan Digital Sky Survey. Those are 5 bands, UGRINZ. The Sloan telescope is in New Mexico, and it didn't do the whole sky, but it did a rather large chunk of it. So not everything is in there, but there's a lot of things that are in there. Then everything else that we've got is various flavors of infrared. 2MASS is the 2 micron all sky survey. That's in JH&K, which is near infrared, 1 to 2 microns. Infrared WISE, Wide Field Infrared Survey Explorer, 3.5, 4.5, 12 and 22 microns. Another infrared set is the SEIP, the Spitzer Enhanced Imaging Products. That is 3.5, 4.5, 5.8, 8, and 24 microns. Spitzer did not do the whole sky, but it did large pieces of it. Akari was a Japanese satellite. It actually had a short wavelength and a long wavelength instrument on it. At this point, we only have the long wavelength images included, so 60, 90, 140, and 160 microns. And then there's IRAS, the Infrared Astronomy Satellite, which is this really old workhorse of a satellite from the 1980s, which was the first all-sky survey, the one with the giant pixels I was showing you earlier. That's at 12, 25, 60, and 100 microns. You can also load a FITS file from any place else at IRSA, off your own computer disk, or off anywhere on the web. Then when you put in what you want, then you search. And this is an example of what it comes back with for M16. You can see by default it's in reverse grayscale. Those are the talons of the eagle. There's the DSS scan photographic plates from the 50s there, and then there's a 1980 versions there. And there's 2MASS from the 1990s, the near infrared. And then down here we've got WISE, which is near and mid-infrared. Up here at the top, it's going to repeat back to you your search in a condensed form. Basically, you ask for this position, this size, these surveys. It's also going to show you the real FITS files. You're interacting with the real FITS files. There's nothing you can break, but you are interacting with the real FITS files. And the tools to handle that are all up here at the top. If you need help, click on the help button there. It'll give you access to the whole document. There's also these context-sensitive help markers throughout these tools, which if you click on them wherever you are, it'll drop you to the right place and help that corresponds to whatever it is that you're looking at. The color table and stretch issues that we were talking about earlier are there. You can see their pull-down menus to make each of the images bigger so that you can look at it in more detail. You can click on that. There's also this button here, which is the 3-color button. If you click on that, it will pick 3 images out of each row and make a 3-color image at the end of each row. So there's an image that it made where it took for red, DSS 1 red, for green, DSS 1, the other way around. Blue is DSS 1 red, green is DSS 1 blue, and red is DSS 2 IR. That's actually not right. It should be blue, red, IR. JH and K, 2MASS is pretty clear because it's only got 3 bands. So J is blue, H is green, and K is red. Then we've got WISE 1, WISE 2, and WISE 4. We got SEIP in there, so it's using IRAC 3, IRAC 2, and IRAC 1. There's Akari, and there's big pixels from IRAS. So note that Akari and IRAS have relatively low spatial resolution compared to these other surveys. So there's lots of cool things in here. If you want to download them so that you have them on your own computer disk, click on download, and you'll be given a choice. Do you want the FITS files? Do you want to save that as an HTML page? Do you want a PDF? The tool is called Finder Charts. Some people do generate finding charts to take the telescope, so that's why we have PDF as a choice. And then there's PNGs where you can, so the FITS images are going to be the original, with the header and 1 color just one filter in the FITS file. PNGs are going to be basically a screen snapshot, what you're looking at. So any overlays that you add, the colors and stretches that you've chosen, that will be preserved if you pick PNG, but you're going to lose the binary information that you would have with the FITS file. So some things that you could try and do, pick your favorite object, look and see what's bright and what's faint in each image that is taken across all these different wavelengths. Is the region that's bright in optical the same as what's bright in the infrared? There's a famous catalog called the MSIE catalog. It was designed to be a list of things that Charles Messier knew were not comets. And I'm sure he would be really annoyed to know that the reason we know his name today is because of his list of not comets. But his list of not comets includes many different things, including star-forming regions, globular clusters, and galaxies. And so for each one of those kinds of broad types of Messier objects, go get images across these wavelengths. And I'm betting that if you pick like M31, you're going to need a really big chunk of sky to see it, as opposed to, say, M16, which is much smaller. So you're going to have to play with what size you need. And there are some Messier objects that are going to look very similar across these different wavelengths, and there are some that are going to look very different. If you have your own camera, whether it's a single lens reflex camera or a camera on the back of a telescope, you can make a 3-color image with your image as one of those color planes. But in order for that to work, you need to have the astrometry in the FITS header. So if you need that, you can go to a tool called astrometry.net, not astronomy, but astrometry.net, and then you can add the coordinates into the header of the FITS image. There's a YouTube feed that we run at IRSA that has several different movies on Find Your Chart, as well as the other tools at IRSA. If you are much more interested in planetary imaging, there's a huge, very active community of so-called amateurs, and they play with all sorts of NASA images that are coming straight off the spacecraft. Basically, you get them the same time the science team does. So Cassini's no longer with us, but it would put data out at the same time they delivered it to the scientists. And that's the case for Juno and the Mars rovers and spacecraft as well. So if you are interested in doing that, Emily Lakdawala, who's at the Planetary Society, is a huge advocate for this community, and she has produced many different tutorials on how to work with these images. And so if you're interested in playing with images from Juno, by all means, please go and check that out, because there's lots of really cool stuff in there. So there's a lot of data that are already out there. There's an awful lot that are already available via web interfaces. You don't need to know how to program. You just need to get in there, jump in, and start going. You can get engaged with citizen science, and you can really contribute to actual journal articles as published in the scientific literature. You can, of course, go poke around the archives yourself, and you can get real data. But you do need to know that you need to work with FITS files, not PNGs, GIFs, or JPEGs, and that you can change the scaling in the table, the color table, to be whatever you want, to bring out whatever details you're looking for. If you see something strange in the image, you should not assume it's aliens. It's probably artifacts. And you need to go figure out, you need to go read the documentation, figure out what artifacts are expected. You can, of course, just poke around in the web interface. There's nothing you can break. You're not going to damage anything. You're not going to ruin the integrity of the data. We've got copies of it. You're not going to touch our copies of it. You can just grab it, download it, play with it. You can learn some interesting things about how different objects look, whether it's in the optical or the infrared, for example. There are tons of other archives out there, and there's a very rich community of people that are working with images from missions around other planets in our solar system. So, if nothing else, I suspect your mind has been blown by some of the information that I've conveyed here. So, because I know I went fast, I wanted to emphasize that I've got all of the links that I mentioned collected in one place, and you can get to that by scanning that QR code, or I'll put it in the description of the YouTube video. If you are a high school educator and want to get involved in real research, playing with real data and doing real research, check out NITARP, which is a program that I run that partners small groups of educators with a research astronomer for a year-long research project, all involving real data.